All right, hello everyone. Welcome to another one of Mr. Martin's math videos. This is a video specifically for British Columbia Pre-Calculus 12. We're on Chapter 8 looking at logarithms, and this is the first section helping us to understand logarithms. So, welcome to the wonderful world of logarithms. This is a topic studied in pre-calculus, which at times can give many students a large headache, not because it's hard, but because it's new. But it's also very universal in its application, not only in mathematics, but chemistry, biology, geology, and so on and so forth. I'm sure you've seen a lot of graphs these days that, it can be, in these COVID-19 cases, can be shown as a linear graph or logarithmic scale. So they're using logs to represent data in a different way, right? It helps to identify exponential growth versus linear growth, so it can be useful in all kinds of different applications. Logarithms have a lot in common with exponential function. In fact, they are the inverse of the function. It's a really useful way of seeing these. They are the inverse of the function y is equal to c to the x, which is the function that we learned about last chapter in chapter 7. This unique property can be used to solve what first appears to be very difficult-looking exponential equations. So before we start graphing these and solving equations, let's first get a feel for how logarithms work and how to evaluate them. So what is a logarithm? So let's consider the following statement. 2 to the power of 5 is equal to 32. We know that if we multiply 2 by itself 5 times, we will get a product of 32. Another way of saying this is 2 to the power, raised to the power of 5 is equal to 32. And we can even write it in expanded form here. 2 times 2 times 2 times 2 times 2 is equal to 32. But what if we didn't know what exponent was necessary to achieve the value on the other side? For instance, consider this equation. 2x is equal to 64. Basically, we're asking the question, what exponent could we give to our base 2 that would give us an end result of 64? Answering this question with your current understanding of algebra proves to be difficult. Thankfully, logarithms come to the rescue, often with mathematicians. What mathematicians do is that they convert an exponential equation into a logarithmic form using the following relationship. So here, from last chapter, we're used to these exponential functions, and we can convert it into a log function with this here. Okay, I did want to add this another way that you can think about this. B, you can also do, because some of you guys' calculators, you may be using Ti84, Ti83. The Ti84s, when you go into math, you have the option called log base, which is beside A here. I don't know if there it's highlighted there, log base. However, the Ti83s sometimes don't always have this option where you can put a base number and a larger number inside. So what you can do for that is you can just use the regular log button, and we can see that B is also equal to log C over log A. Okay, log C divided by log A. So in this situation here, you don't actually need the log base. You can just divide the log of C divided by the log of A, and you also get B as well. Okay, so if you're using a Ti83 or you're not figuring out where to use the log base, this is a good approach for you. Okay, and it can actually give us, so let's actually use it to the example that we've looked at here. So 2 to the x is equal to 64. Remember, obviously here you probably figured this out, but a lot of the questions we looked at last chapter, the method that I gave you was guess and check, right? To one decimal place. You just have to kind of keep plugging in numbers into the exponent until you got an answer that was pretty close to the right answer. But here we don't have to guess and check because we can convert the number with an unknown exponent into a log of this form here that equals the x that we're looking for. Okay, and of course here this would also be equal to log 64 over log of 2. Okay, so let's actually prove this both ways so that you see that both approaches are fine, no matter what calculator you have. Okay, so first, log, I'm going to use the function log base. Okay, my base is 2, and the number here is 64. I put in, I press enter, I get 6. X is equal to 6. All right. The other way I can put it is I can just press the log button in the home screen, log, and then of 64, I need to close my bracket, divided by log of 2. And I get the same answer. Okay, so both of these methods will give you the correct answer. So whatever method you want to use is fine. Okay, as long as you are using the right conversion. Here you have this conversion in your formula sheet. Okay, you can add this one to your formula sheet as well. That is fine as well. Okay, so both the ways, and both of those then allow us to know that this exponent, so this is actually 2 to the 6, is equal to 64, right? That's what this allowed us to solve for sure. And when this whole numbers like this with with 2 as a base, you probably could have figured it out on your own. But when you're dealing with decimals and exponents that are in fractions or exponents that are irrational numbers, for example, it's hard to guess those. And so this gives us a method to solve these with precision. So we've converted an exponential equation into a logarithmic form. This statement, log 2, 64, basically asks the question, what exponent do I need to give to the base of 2 in order to get 64 as my answer? Okay, that's what this is saying. Okay, this is saying this. All right, another thing to note is that the expression log 2 to the 64 is the exponent of the equation 2x to the 64. This is because it gives us the power to isolate variables that are stuck in exponent, right? So because log, let me make my cursor a little bit bigger here for both. Because log 2 to the 64 is equal to x, then, essentially what you're saying is 2 to the power of log base 2 to the 64 is equal to 64, okay? Because you're substituting this number. So I'll write it in red since I typically write my substitutions in red, okay? Because log 2 to the 64 is equal to x, okay? Which is exactly what we end up getting. All right, so this is kind of the key for this chapter right here. A to the b is equal to c. Log base of a to the c is going to give you that exponent b. So let's put this to work here. All right, let's see if we can solve some of these by hand. You'll always have your calculator double check your answers, but a lot of these we can solve by hand because this conversion, a to the b is equal c, to log a to the c is equal to b. This is a two-way street, right? We can go back and forth, and sometimes it makes sense to go back and forth when we're given a log, and we can solve for what the log represents by converting it back sometimes, or just plugging it into our calculator, right? Of course, this could also represent. Not represent, but b is also equal to log c over log a, right? That's the other one you could use here. So you can use this. If you have a Ti84, I suggest using this one. If you have a Ti83 and you don't have that log base, or you don't know where that you can't find it, for Ti84s, you just press the math button, and then it's right there. Okay. For Ti83s, anyways, if you know where it is, post it in the comments. But otherwise, you can just use this here. Okay, log c over log a for you guys. It's also equal to b. Okay. All right, so in this situation, for evaluating these, of course, we can just go in our calculator and plug math log base log 7 to the 49, press enter, that's equal to 2. Okay. However, we could also convert it to more of an exponential form and see if we can determine an answer from there, right? And for now, it's going to be helpful to do that just so that we can get our feet under us a little bit with these exponential and logarithmic functions. Okay, so here, log here, I have that 7. A is equal to 7, B is equal to 2, and C is equal to 49. Okay, so if I were to convert back, A would be 7, B would be 2 is equal to, or here, I won't put this here. I'll say that 7 is, B is unknown. All right, and C is equal to 49. Okay, well here, can we simplify one side to get the answer of B? The answer is yes, right here. If this was 7 to the B is equal to 7 squared, right? We can substitute 49 with 7 squared. Therefore, that tells me that B is equal to 2, which is exactly what we got in our calculations when we just plugged it in. Okay, so that's kind of two approaches here. Here, same thing, right? A is equal to 6. C is equal to 1, and B is unknown. If I put it in exponential form, I get 6 to the B is equal to 1. All right, what exponent would B have to be in order to make 6 equal to 1? Well, that's 0, right? 6 to the B is equal to 6 to the 0. Therefore, B is equal to 0. And again, I can plug it in here using the other method, log 1 divided by log 6. You might prefer this method, even if you have a Ti83 and have the log base approach. You might prefer the second notation, what we just did, instead of using the log base. It's up to you what you use, just as long as you can use it consistently and correctly. That's all that matters. Okay. This one here, log to the 0.001. Think, what is the base of a logarithm? Okay, this is known as the common base here. Notice that, and this in our calculator here, when I just press log here, it doesn't mean that there's no base in log bracket here, okay? It just means that it's the common base. Just like when we do square root, that's the common root, so we don't write the 2 as the index. But if you do cube root or with an index other than 2, you have to write the number. This is the same thing. This is the common logarithm. And what that means is that this is actually logarithm of base 10, 0.001, okay? But this is unnecessary because it is the common logarithm. It's oftentimes omitted in the notation, all right? So just so you know, the common logarithm is log to the 10 and then to the C, okay, is equal to B. All right, that's what they're dealing with there. All right, so if I were to put this in exponent form here, I have A value is 10, my C value is 0.001, so 10 to the X is equal to 0.001. So here, I should be able to figure out that this is 10 to the negative 3, therefore, oh, sorry, I shouldn't use X here. I should use B. So B is equal to negative 3. And if I plugged in just log 0.001, I would get negative 3. Same answer. Okay. Last example here. This one's a little bit different because I have some square roots involved. All right. And so in this situation, I have A is equal to 2 and C is equal to 4 root 8. Okay. And B is unknown. So if I have A to the B is equal to C, 2 to the B is equal to 4 root 8. Okay. Right now, I still not able to tell what B is. However, I can switch what's on the right-hand side. I can substitute to get a base of 2 on the right-hand side. So this is 2 to the B still. I'm going to substitute the 4 with 2 squared. And I'm going to substitute the root 8 with 2 to the 3 over 2. Okay, if you guys remember some of the dealings with square root we did in the past, right? Essentially, square root is just 8 to the 1/2. Maybe I'll do it in a couple steps here, or I'll show my steps here. This is equal to 8 to the 1/2, okay? And then I change the 8 to, I'll just write it next to it instead of rewriting it. Then 8 to the 1/2, I substituted 2 to the 3 to the 1/2. 2 to the 3 I substituted in the place of 8. And then I multiplied 3 times 1/2 gives me what I got here. Then it's a power of product of powers. So 2b is equal to, and I just add the exponents because they have matching bases, which gives me 2 to the 3.5. So I know that b is equal to 3.5. All right, and if I were to just plug it in here like this, math log base 2 and then 4 root 8, I would get the exact answer, 3.5, to confirm. Okay, but I definitely, for these ones here, eventually you'll just be able to plug them into your calculator. That's fine, and it's important that you know how to do that as well. But I do want you guys to do both methods, okay? Check your answer by plugging into your calculator, but I want you guys to change these into the exponent form first and see if you can figure that out without your calculator first, okay? It'll just get you guys more familiar with converting between exponent form and logarithmic form. All right, so go ahead and pause the video and give these a shot on your own. All right, hopefully that went well for you. All right, let's take a look at these ones here. So again, a is equal to 2, c is equal to 32. So if it's a to the b is equal to c, 2 to the b is equal to 32. And then 2 to the b is equal to, I can substitute 32 with 2 to the, what do they have in the 5? Making b equal to 5 as my answer. Whoa, let's fix that there. All right, and of course I can confirm that with my calculator, whatever method you want. I'm just going to use this method here, log 2, and I get 5, exactly what they got there. Let's try this one here. A is equal to 9, c is equal to 5 root 81. So again, if this is still true, then it's 9 to the b is equal to 5 root 81. And then I'll work on my substitutions here. This becomes 81. 1 over 5. Okay, the index becomes the denominator. All right. And then I'm going to substitute 81 with 9 squared. And I end up finally with 9 to the 2 over 5 is equal to 9 to the b. Oh, sorry, that's a 2. 9 to the b. Therefore, because they have matching bases, the exponents must be equal to each other. That was all of last chapter, pretty much. We determined that. Therefore, b is equal to 2 over 5. And I can use my calculator to confirm that. Base of 9. And then here I have x root 581, enter 0.4, which is 2 over 5. So we're good to go. Log, okay, again, remember this is log of this. This is log with base 10, right? So a is equal to 10, c is equal to 1 million. Okay, and this could be written as 10 to the 6, which might be beneficial here because when I put it into the a to the b equals c, I get a to the b, or sorry, I get 10 to the b is equal to 10 to the 6. Therefore, right away, I get my answer of b is equal to 6. Okay? And double check with my calculator, and I get 6 as well. And last one here, similar to previous question that we saw, a is equal to 3, and c is equal to 9 root 3. All right, so I get 3 is equal to b, and I substitute 3 is equal to 3 to the b is equal to 9 root 3. Okay, 9 root 3 is equal to 3 squared times 3 to the 1/2. All right, and then I add those two together, which gives me 2.5. 3 to the 2.5 is equal to 3b. Therefore, b is equal to 2.5. And there's your answer. And 9 root 3, close bracket, divided by, delete, divided by log of 3. And there's your confirmation. All right, good. Hopefully that went well for you. All right, rewatch anything that you might not have gotten correctly. All right, and let's go to other examples here. Okay, again, determining the value of x by converting between logarithmic form and exponential form. All right, so again, here now I have my a value is 5. My b value is -3, and I don't have my c value, right? So then I can convert here, again, using my equation. A to the b is equal to c is can be converted to log a to the c is equal to b, right? And so that's how I determine my values. I'm going to plug those in. So 5 to the -3 is equal to x. Okay. And then here, 5 to the -3, x is equal to 1 over 5 cubed. And then, which is equal to 1 over 125. Okay, if you were to get rid of all of the powers. Okay, let's try another one here on the right. Again, this one I don't have a. A is equal to x here. B is equal to 2. C is equal to 36. So here I have x squared is equal to 36. All right, well, what number squared is equal to 36, right? Well, x squared is equal to 6 squared. Therefore, x is equal to 6. Okay? And last one here, I have a is equal to 64, b is equal to 2 over 3, and c is equal to x. So I can substitute these in. I have 64 to the 2 over 3 is equal to x. Here it might be helpful to turn this into a root, cube root or whatever. So this would be cube root of 64 squared. Okay, if you look at the cube root of 64, cube root 64, that is equal to 4. So this is 4 squared is equal to x, so 16 is equal to x. All right, so that's, again, how to use this going back and forth between log and again, of course, you can also write it as log c over log a, but going back and forth between logarithmic form and exponential form to solve for these equations. Go ahead and pause the video, try the letters on the right here, D, E, and F, and then we'll come back together and finish these off. All right, hopefully that went well for you. Let's get to work. So a is equal to 4, b is equal to -2, and c is equal to x. So that means that 4 to the -2 is equal to x, which is 1 over 4 squared is equal to x, which is 1 over 16 is equal to x. That's your final answer. Here, a is equal to 16, b is equal to -1 over 4, and c is equal to x. So again, here I have 16 to the negative, and 16 to the -1 over 4 is equal to x, and then this is 1 over 16 to the -1 to the +1 over 4. That's the point of bringing it to the denominator, is equal to x, and then 1 over 4 root 16 is equal to x, and then x is equal to the 2 is what it's equal to. Oops. So 4 math x root 16 is equal to 2. So I get that denominator is equal to 2. So I get 1 over 2. 1/2 is equal to x. And last one here, a I do not know. A is equal to x. B is equal to 2 over 3. And c is equal to 9. So I get x is equal to 2 over 3 equals 9. Yeah, in this scenario here, I just kind of have to, you can change this up here for the roots and whatnot. You can change this as a cube root of x squared equal to 9, and then you can actually do some algebra left to right, right? You can square root both sides, which gives you cube root of x is equal to 3, and then you can cube both sides, which makes x is equal to 27. All right, so that's an approach there for you guys. Okay, so hopefully that went well for you. Some of these are a little confusing. Again, confirm with your calculators as you're doing these. Let's talk about the graphs. Okay, example 3, graph the inverse of an exponential function. Write the exponential equation of the inverse, y is equal to 3x. Okay, well, we know for inverse you just switch the x and the y. So here you can write this equation as x is equal to 3 to the y, okay, which could also be written in logarithmic form as y is equal to log base 3 to the x, okay, so that we're back with a y equals equation from the inverse exponential function. So again, proving that the logs here are truly the inverse of the exponential function. Okay, so let's see what that looks like if you graph it. So our first one here, of course, this is the equation y is equal to 3x. Okay, so if I put 0 in that exponent, I get 1. If I put 1, I get 3. If I put 2, I get 9. If I put 3, I get 27. So let's plot those points in on my bluish green here. So 0, 1, 1, 3, 1, 3. It's a strange scale here. 2, 9. is that 1, 3, 1? Yeah, no, that's 1, 3. And then 327, so it jumps up by quite a bit. 3 and 27 right here. Okay, and you essentially get this graph that goes actually along the line, and we'll graph it in our graphing calculators as well to kind of help clean this up. All right, and now for the other one here, where I have y is equal to log 3 to the x. So for the purpose of getting good values into our graph, we're going to use some different input values here. I'm going to input 1/3. I'm going to put 1, 3, and 9. Okay, so I'm going to put these in. So if I put in 1/3, so if I do math log base 3 and then 1 divided by 3, I'm going to get -1. If I put 1, I get 0. If I put 3, I get 1, and then you're essentially switching the x and y values as well, right? So 3 is 1, and input of 9 would be 2, right, when you're going at inverse. So these would show up. So 1/3 and -1. So 1/3 and -1 would be something here. Then 1 and 0 would be here. Then 3 and 1 would be here. And 9 and 2 would be here. And then we can even go 27 and 3 would be another point that we could put on this. Okay, 27 and 3. 27 would be here, 3 here. Okay, so you get a similar line kind of curving. Okay, and we know as well on graphs, okay, their reflection, an inverse graph is a reflection upon the xy axis. Okay, it's a reflection on the x is equal to y axis on your graph. All right, so now some characteristics of the inverse graph. Okay, the log graph specifically. This is the one that we're answering these bottom questions for. Okay, this is the y is equal to log 3x. Okay, so here, domain and range. Okay, so for domain, I have x is not going to be less than or equal to 1, so I have x is greater than 0. That x equals 0 is actually an asymptote. We can write down here x is equal to 0 is actually an asymptote. And then, of course, because it's a solid line, x represents the reals, and for the range, y is just all reals. Okay? The x-intercept, where does across the x-intercept, is at 1 and 0, that coordinate for the x-intercept, and then the y-intercept, there is no y-intercept for this line. Okay, this line will continue along the asymptote, but never cross it. Okay, just like an exponential line would not cross the x-intercept, the x-axis, the inverse of that would not cross the y-intercept or the y-axis. All right. Last page here, looking at an application. Of course, in Vancouver here, we're always expecting the big one in terms of an earthquake. Heaven forbid it would happen right now. But here is an application of logarithms. So in 1935, American seismologist Charles R. Richter, you may recognize this name because we measure earthquakes on the Richter scale, developed a scale formula for measuring the magnitude of earthquakes. The Richter magnitude, M, of an earthquake is defined on the log scale. I shouldn't circle that. Let me highlight it instead. M, the magnitude, is equal to log A over AO, where A is the amplitude of the ground's motion, usually in microns, measured by a sensitive seismometer, and AO is the amplitude corrected for the distance to the actual earthquake that would be expected for a standard earthquake. So in 1946, an earthquake struck Vancouver Island off the coast of BC. It had an amplitude that was 10 to the 7.3 times the AO. Okay, the amplitude corrected for distance had a standard of the standard earthquake. What was the earthquake's magnitude on the Richter scale? Okay, so just one note before we solve this problem. The parameter AO represents the amplitude of a standard earthquake. By definition, this is an earthquake that can be felt 100 kilometers away with amplitude of 1 millimeter. This has a magnitude of 3 on the Richter scale. Okay, so in this situation here, I can start off with my equation, right, which is m is equal to log A over AO. Now here, because they give me the value of A as a function of AO, I could substitute that in my log equation. So this is equal to log, and then I'm going to substitute inside log here. This is in the brackets of log. Instead of A, I'm going to do 10 to the 7.3 times AO, okay, over AO, which actually works out nicely here because the AOs get to cancel out, and I'm left with log of the 10 to the 7.3, which, if I were to plug that into my calculator, is equal to 7.3. Okay, so that's the magnitude. So there was an earthquake of 7.3. You know, if you ever watched the news after an earthquake hit, oh, it was a magnitude of 6.4, a magnitude of 2.5, right? And we get a false sense of the scale because it's a logarithmic scale. We think of an earthquake of a magnitude of 4 and then a magnitude of 8. The magnitude of 8 is like twice as strong as the 4, where that's not the case at all. Okay, the magnitude of Richter scale of 4 versus the Richter scale of 8. A magnitude 8 would be 10,000 times as powerful as the one with the magnitude of 4. Okay, so it's kind of a deceiving scale, but it's just not practical to have a linear scale for these types of measurements. So the Richter scale is still very useful. All right, the strongest recorded earthquake in Canada struck in Haida off the coast of BC in 1949. It had a Richter scale reading of 8.1. How many times as great as AO was the amplitude? Okay. Well, here, if I have magnitude, again, m is equal to log A over AO. If this is an amplitude of 8.1, is equal to log A over AO. I can change this into exponential form because the base here, because there's no base, it's a base of 10, right? You gotta see that. This is a base of 10 everywhere here. This is a base of 10. Base of 10. It's the common base everywhere. So this becomes 10 to the 8.1 is equal to A over AO. And if you were to multiply AO on both sides, you'd know that the magnitude of this earthquake was AO times, it was 10 to the power of 8.1 times greater than the magnitude of AO, okay? Just based on this statement here. Okay, lastly, we want to compare the two, how many times greater was the amplitude of the earthquake in Haida, that of the earthquake that struck Vancouver Island. Okay, so now here, this is where we want to take their comparisons based on AO, the common earthquake there, the standard earthquake. And so if you had the you cannot just take 8.1 divided by 7.3 here. Okay, this does not equal how many times greater, right? If I just did this, 8.1 divided by 7.3, oh, it was, is just 1.11 times greater. It's almost the same thing. It's just a little bit stronger, but that's not the case at all on the Richter scale. What you actually have to do, so this would be the wrong approach. What you actually have to do is take the magnitude and exponential form of the two, 7.3, okay? And again, if you remember your exponent rules, this is a quotient of power, so 8.1 minus 7.3, which is equal to 10 to the power of 0.8, which is 6.3 times greater. Okay, so just that small difference of 0.8 on the Richter scale means that the earthquake in Hawaii was over 6 times more powerful than the earthquake that struck Vancouver Island in 1946. Okay, so a little bit of knowledge on the Richter scale there. Homework here, due Monday. Look for the video and submit on Teams using a scanner app. If you have any questions, put it in the comments or in the homework channel. And I'll see you next time. Goodbye.